Hello all, welcome to techGig webinar. The topic for today's webinar is how MPLS IPVPNs help reduce costs for service provider customers. It's my privilege to introduce our expert speaker, Mr. Raghu Srinivasan, Senior Manager at Brokerage Communications to you all. Raghu is responsible for the MLX XMR service provider routers. As a technical lead, he has been involved in implementing IPVPN solutions in service provider routers in his earlier companies. Dear participants, during the session you can post your questions in the chat pane available. So, without taking much of all your time, I welcome Mr. Raghu to take the session ahead.
Hello everybody, are you able to hear me? Hello?
Hello, yeah, your voice is coming, but it's very low.
Hello, are you able to hear me?
But your voice is very low. Can you please be more loud?
Okay, now is it better? Now is it better?
We can go ahead now.
Are you able to hear me now better?
Yes, your voice is coming fine now. Thank you.
Okay, so is it something that we can start?
So we can start now.
Okay, so are you able to see the screen as well?
Your screen is visible.
Okay, alright. So let's get started. First of all, I would like to thank you all for taking some time off to listen to how MPLS VPNs help reduce costs for service provider customers. My name is Raghu. I'm a senior manager at Brokerage Communications, where we're working on service provider routers. This is one of the services that we offer on our routers. This presentation will not be talking about any company-specific implementation, but more about the general concepts that you can understand, appreciate, and see how people can leverage this service to make money. Right? So some of the key questions that we are going to be answering as part of this presentation would be, how do you ensure security to the customer traffic? Now there are different customers taking service from the same service provider. They don't want the traffic to intermingle with each other, so there needs to be some kind of a security arrangement that has to be there. And then we know the current problem that we are facing in the IP domain, which is the depletion of the IP addresses.
Hello, sorry for interrupting.
So we'll see how this.
There is some background noise which is causing the voice to be very low.
Okay. I'm not able to hear. Is it better now?
The background noise is still coming. Can you please take the mic settings?
The mic setting should be. How about now? Is this better?
Now it seems much better.
Okay.
Thank you.
Yeah. Yeah. So as I was saying, currently one of the problems that the IP domain is facing is the depletion of IP address space, and IPVPN solution does mitigate the problem to some extent by allowing different customers to use the same IP address. We'll see how that is how that happens. And then we'll talk a little bit about the MPLS IPVPN architecture itself. It's going to talk about how BGP helps us in providing this particular solution. Then we'll talk a little bit about IPVPN lite as well. There are many situations where the customers will not have access to MPLS. So what is it that they do in that context? And then we'll also look at some of the deployment and service models for IPVPN, which can be a significant cost advantage for not only the service provider customers but also for the service providers. Some of the assumptions that I'm going to make is that the listeners have an understanding of the routing protocols like BGP and OSPF, and they have some knowledge of MPLS at a high level at least, and then they also have a knowledge of the service provider network. If you have any questions, we can answer them towards the end of this webinar, where I can answer all the questions. But at a high level, I expect that you would have an understanding of these so that you can understand and appreciate some of the cost-saving things that we're going to talk about. So let us first start off with the main thing on the agenda, which is what is the need for IPVPNs. So typically we notice that there are geographically dispersed IP networks that need to be connected for transparent and secure private IP connection. An example would be a company A buys over another company B, and then these two companies' network will have to be integrated in a fashion wherein they can act as if they are on the same private LAN. So they are geographically dispersed in their locations, but you have to treat them as if they're going to be on the same LAN. That is one of the things. And then as companies have grown over the years, the customers have invariably found that it is much more cost effective to buy IP services from the service provider rather than manage everything on their own. If you look at the history of how networks have evolved, you'll notice that a lot of the customers wanted to manage the network on their own, and so that was a very expensive thing. But now you can buy these services from the service providers, and they'll also ensure security. So it's a much better, it's a big cost advantage for both, right? And another motivation for using IPVPNs is the reuse of the service provider hardware. Earlier, the service provider used to build huge networks, but then the extent to which the huge networks were being leveraged were not as much. I mean, it was not cost effective for the service provider as well. We will see how in this particular IPVPN deployment scenario, the service providers are able to reuse a lot of their hardware. They are able to cater to multiple networks to provide this IPVPN service. And the next motivation is QoS, which is one of the most important things for any customer. He's going to pay the money to the service provider based on some QoS, and we have to see how the service provider is going to help him achieve this particular QoS. It's part of the service level agreement. If you see how networks have evolved, earlier there used to be one network which the service providers used to build for ATM alone, another network for frame relay, another network for IP and things like that. A typical example would be a company like AT&T or Verizon. They used to have 3 different networks, and then they used to offer different kinds of services based on the type of technology that was used at the customer premises. But once MPLS came along, there was a move towards a converged solution, which is a single MPLS core. And the service provider immediately used this to provide different, to provide services to different kinds of access technologies, whether it is voice over IP, whether it is Ethernet, whether it is traffic coming from the DSLAM, or whether it is ATM. It doesn't matter. You have one edge switch which could aggregate all this traffic and then send it over one MPLS core. So with one particular network that the service provider built, he could provide different kinds of services to different customers. So this is a huge advantage and cost savings for both. If you go back to the history of how networks used to be built, I mean, let's call this as legacy VPNs, right? This is how AT&T used to build their network. The layer 2 technology that was being used was ATM or frame relay, and they used to build a full mesh topology wherein all the customers belonging to a particular VPN were connected to each other, and there were some of different problems when a new site had to be added. If you see the screen, if a new site had to be added, the new site had to be connected in a full mesh to all other customer routers. So this is a huge burden for the service provider. So this is a typical case where one company buys another company and it has to integrate it as part of its network. But this was how typically networks used to be built out. One of the requirements when you build an IP network based on an ATM frame relay core would be that you have to have a full mesh of the virtual circuits. Every time a new router is added, the new circuits must be provisioned between this router and all of the routers in the core. And the routing also used to be a huge problem for the customers. There used to be large amount of routing traffic if OSPF or ISIS is in the core, because one of the requirements of routing is that everybody should be able to reach everybody else. So whenever there's a new router that is added, there is a significant amount of routing traffic within the network. And the provisioning of circuits is also complex because it is very hard to predict the exact amount of traffic between two routers. Now, when a company buys another company, it is very difficult to predict what kind of traffic that the company is going to generate, or what kind of new technologies they would adopt, so that the amount of traffic that they are going to generate is going to vary. So it is very difficult to provision this kind of service in the network. There are other ways the different companies tried to provide this service earlier, which is one of them is this policy-based routing, wherein you would say just based on some criteria, you do the forwarding of the packets. Basically, what is the idea here? Every customer set belonging to a particular VPN wants to talk to everybody else. So they could define these kind of policies at the edge of the service provider network and say for all packets coming from this VPN, you just send it across to the particular egress node. But then since these kind of forwarding is not based on the destination router but based on some particular QoS, there could be a lot of forwarding loops. I mean, you are not leveraging the power of the routing protocols to prevent these kind of forwarding loops. Not only that, if you have to ensure a particular QoS along the path from the ingress edge node to the egress edge node, every router along the path had to be configured to honor the particular QoS. So this is a very cumbersome and problematic scenario for the service providers. So in summary, some of the issues that the legacy VPNs had were that the existing service architecture limits the carrier's ability to expand into the growing advanced IP services market. So once IP services evolved, the service providers were not able to leverage that as much as they would have liked, because they were building different kinds of networks with different technologies. So multiple architectures required for layer 2 and layer 3 services. You had to buy different kinds of equipment as well. And depending on the access technology that is being used by the VPN customers, there used to be only one single access technology per VPN. An example would be a service provider would be using, say, ATM network only, and some customer would be using only frame relay services. So these are problems that the service provider could not solve very easily. They had to have one single access technology per VPN. Not only that, if you know that ATM as a technology always lagged behind IP technology, mostly because it is built around segmentation reassembly, and there is a severe penalty that you pay for that. As you know, ATM cells are all fixed 53 byte cells, so always cutting down the packets into that size and reassembling it, it's a very expensive operation, right? And then there was also not so much resiliency that you could build to the network because of the high concentration of circuits to the core. We saw what amount of provisioning need to happen whenever a new site is added to the VPN. and it's extremely labor intensive in the sense that the service provider needs to train a lot of people to understand how networks have to be built and then teach them how to provision the circuits and things like that. So it's a very expensive operation to build not only the networks but also the workforce to understand and deploy the networks so that you can leverage the capabilities of the network. So next, so that is basically the motivation for building IPVPNs. Now let us look at some of what VPN and its properties are. What is the definition of a VPN? So a VPN is nothing but a private network service built on a service provider shared infrastructure. What is the virtual part of this? It just means that it appears to be a separate physical network to the customer, but actually it is sharing the hardware resources of the service provider. Then what exactly private means? Each VPN customer maintains its own routing information. The VPN customers are not even aware that there are a lot of other customers who are leveraging the same service provider resources. So they feel that they are on a private network. So that's basically the definition of a VPN. As we talked about, the key drivers are the cost effectiveness, the flexibility, and the simplification. VPNs, as we'll see in the next few slides, they can be built at layer 2 as well as layer 3. We'll see the pros and cons of both these approaches. So what are some of the key features of VPNs? Let us look at it from the viewpoint of a customer who is buying VPN service from a service provider. Basically what he wants is one routing domain per VPN, and he should be able to use any routing protocol. If the customer is always using OSPF, he would prefer to continue to use that. If he's using RIP, he wants to continue to use that. Things like that, right? If he's using BGP, he wants to continue to use that. He cannot change the kind of network that he has just because he wants to buy the VPN service from the service provider. So you need to retain all that. And then the customer would want the flexibility of using his own route maps for transferring routes from one place to another. He wants to build intranet and extranet kind of services. And a typical example of this would be that you can go to any company's website and you will see only that information that is really consumable by the public, not any something which is proprietary to the company, some information that you should not be able to see. And the VPN customer also wants to have firewall capabilities, in the sense he wants to be able to control what kind of traffic comes into his network and things like that. And it's also that the VPN customers want to reuse some of their existing IP addresses. If there are different VPN customers, the service provider can build a network in such a way that both the customers can continue to use the same IP address. It won't affect anything. We'll see how that MPLS IP technology helps achieve this particular thing. Then the most important thing is security, where it should not be possible for one VPN to access the resources of another VPN. This is one of the most important things that all VPN customers look for. And then another key feature is that the C routers need not be routing peers. I mean, this is mostly applicable in the peer-to-peer model. And the VPN customers also want the flexibility of having their own kind of QoS depending on the requirements. Like, for example, if a company wants to connect the head office to its branch office, it might want a different kind of QoS versus a bank which might want to do some wire transfer to some of its branch offices. So the kind of requirements for QoS are different. And here we notice that the layer 1 and layer 2 resources are now administered by the service provider. So what are the different models of IPVPN that a service provider can adopt to provide these kind of services? So typically there are two models. One is the overlay model, wherein the service provider provides only emulated lease lines to the customer. And the second model is called as a peer-to-peer model, wherein the service provider and customer exchange layer 3 routing information, and the provider relays the data between the customer sites on optimum path without the customer's involvement. At a high level, let me tell you what the differences are. In the overlay model, basically the service provider is saying that, hey, here, take one lease line. It could be an ATM circuit, it could be a frame layer, or whatever that might be. He's providing layer 2 services, and he's going to map that onto his MPLS within his network. And all the routing problems are basically the concerns of the VPN customer. So a lot of customers prefer that. Now there is, in the peer-to-peer model, what happens is the customer will say, hey, look, I just want to be able to deal with problems on my direct connection to the service provider, and it's your responsibility to connect me to my remote sites. So basically the routing problems are the problems of the service provider now, and it's not the customer. Now both these approaches have its pros and cons, and let's see what they are. So in the overlay model, as I said, there is a clear separation between the customer and the service provider's responsibilities. The service provider provides the customer with emulated lease lines called virtual circuits. In this particular case, the service provider has no knowledge of the customer network, because all he's concerned is, I'm going to provide you a lease line and I'm going to charge you for the amount of usage. And it is the job of the customer to establish its communication to all the remote sites over these particular emulated circuits, and the routing protocol data is exchanged between the customer devices. As I said, the service provider has no knowledge of how the customer has built the network, how many routes he is using, and things like that. So the billing is purely based on the lease line that he has provided to the customer. In this particular case, it is hard for the service provider to provide multiple classes of QoS because it cannot differentiate the traffic in the middle of the network. One thing we have to be careful here is in understanding this particular scenario is that the service provider is providing the service to multiple customers. So since he's not aware of the kind of traffic, he'll not be able to optimize his network. Right? So that's the most important thing to keep in mind. So how does this work? So this picture here on the slide gives a nice demonstration of how this particular feature works. So here, if you see, there are different layer 2 VCs which are going to each of the different customers. There's a pink line, there's a black line, and there's a brown line. They're all going to 3 different customers from the edge router. So that's the service that the service provider is going to give to the customers, and he's going to charge them based on the usage basis. And what you see in the circle in the blue is nothing but the service provider network, and this is MPLS based. So the service provider is going to build tunnels from each of the edge nodes to all the other edge nodes. So in this case, it is from P on the left to the P to the right. So you can see that the tunnel is represented in green. Now, how does he provide the connectivity for the different customers? You can see that the pink circuit is mapped all the way from one end, from ingress P to the egress P through this tunnel. The same thing with the black circuit as well as with the brown circuit. So a representation of that, if you want to see, if you see below, the tunnel label is nothing but the big pipe, and it is going to carry the services of each of the customers in different colors. So within the tunnel, you are going to provide services to each of the different customers, ensuring that there's no interaction amongst the VPN traffic, and you can also charge them based on the QoS provided by the tunnel. So this is typically how a layer 2 VPN services are provided to customers by the service provider. Another illustration of the same thing is if you are providing L2 service to the customer, you can see that the packets are coming from the C to the P, and the L2 services get mapped onto the LSP. LSP is nothing but a label switch path which the MPLS code allows you to build. So you can see that label switched path is built there, and different packets belonging to different customers are going through that all the way to the egress edge router, where a legacy L2 frame is preserved all the way through the tunnel, and from there you know who are the HCE nodes to which you have to transport the service to. If you have followed the MPLS forum, you'll notice that Martini is one of the authors for providing this model of layer 2 service, wherein all services look like a virtual circuit to the MPLS network, and the provision service is associating each endpoint with a common VC ID. And networks automatically determines the VC label and the tunnel label to push on an L2 frame. So basically you have one bigger L2 LSP tunnel within which there are multiple small tunnels, each one representing a different VPN customer. Why would companies deploy this kind of topology? Typically when they have to build a hub and spoke kind of a topology, wherein if a remote sites talk only to a central site, it is possible that a lot of companies with head office in one place, branch office in other places, they want this kind of a model wherein everybody talks only to the head office. So this is an easy way to deploy this kind of a service. Then there is partial or full mesh topology, wherein you want every site to be able to talk to every other site directly rather than going through one central site. So in which case you can prefer to build a full mesh topology. And then there are situations wherein you might want a combination of these two, which is the hybrid topology, wherein you might have your all the sites into three different categories. One is the access networks, wherein you want everybody to talk to everybody else, but only within the selected access networks, and then you can aggregate from there on to a distribution and then on to a core. So this is useful when you want to reduce the amount of controlled traffic. So this is another topology wherein they might prefer to go for this layer 2 VPN services. Now the second way they can deploy a VPN, let's talk of some of the problems of this overlay model. So this is well suited for non-redundant configurations with a few central sites and many remote sites, but it becomes extremely hard to manage in a more meshed configuration. If you notice that most service provider customers, they're always looking for redundant configurations. In case there's a problem with one circuit, they want all the data to go on a different circuit. So in such situations, to build a complex topology and mapping all their emulated circuits onto LSPs becomes a huge problem. And you need to be able to do proper provisioning of the VC capacities. You should have a detailed knowledge of the site-to-site traffic profiles, which are usually not readily available. If implemented using layer 2 technology, it is quite complex to migrate to IP-based networks, and the routing also is complex because you have put all the burden onto the customer. So these problems are something similar to where you had only ATM network or frame rail network, except that here you have converged them all onto just one MPLS network. So it is not so bad because the service provider is using only one MPLS network. However, it is still a problem when you have to take care of routing. But then, not to say that this should not be deployed. A lot of customers prefer this kind of deployments for the way their company is. So this should be fine. So next, let us look at the peer-to-peer model. So in this case, typically the customers do not want to bother about their inter-site connectivity. if we are talking of a company like, let's say, Reliance, they will have an office in pretty much every single city in India. So it will be difficult for them to kind of build direct communication with all the remote offices. Instead, they are better off taking the service of one service provider who can connect them to all the remote offices. So in this case, what happens is the edge directly exchanges routing information with the customer edge router, and the service provider routers exchange customer routes through the core network. The customer can outsource the routing to the service provider, thus saving cost. Which means here, the concern of the customer is just talking to the service provider, and it is the job of the service provider to build connectivity to all the remote sites. So it is a significant cost savings for the customer because he has to only worry about one link, which is directly talking to the service provider. He doesn't have to worry about talking to the remote sites. That problem and burden becomes that of the service provider. So a typical example when customers would prefer this is when they want to build an extranet kind of a topology, wherein you want two different organizations exchanging common data, or you can build central services extranet where for linking multiple organizations with similar interest. So extranets become a lot more centralized, or you can also use it to build intranet. You can see that there are multiple advantages if you go for the peer-to-peer model, wherein the routing is very simple because the customer is only concerned about exchanging the routing information with one or a few peer routers. If you want redundancy, then you might want to peer with two peer routers, right? And the routing between customer sites is always optimal, as the provider routers know the customer network topology and can thus establish optimum inter-site routing. Basically what this means is that the service provider has good knowledge about the kind of routing traffic within his network, because it is his job to provide the inter-site community. So he can come up with all kinds of optimizations within his network to best leverage the resources that he has. The bandwidth provisioning becomes simpler because the customer has to specify only the inbound and outbound bandwidths for each site and not the exact site-to-site traffic profile. So this is a huge thing in terms of cost for the service provider, because he clearly knows what is the kind of inbound and outbound bandwidth that each site needs. And then addition of new site is simpler because, say, a company buys company A buys another company B. Now all they have to do is make sure that they are talking to the same service provider. That's all they need to worry about. It will be the job of the service provider to build connectivity across these two. So there again, it's a significant cost advantage for both the customers as well as for the service providers. So that is at a high level about the different models. Now let us get into some of the technical details of how MPLS VPN architecture is implemented in these service provider routers. So at a high level, we should be aware of some building blocks as such. We have already talked about this. Generally, C represents the customer edge. P represents the provider edge. P is nothing but the provider core router. And then it is possible that you are taking service from two different service providers. As you can see in this particular slide, there is a corporation A which has three different sites. It is possible that these sites are in different countries altogether, in which case you will have to take the service from multiple service providers to build connectivity across your sites. So just to simplify the understanding of how MPLS IPVPNs work, we'll assume that there is only one service provider cloud, and this particular slide demonstrates how you can build connectivity across the yellow VPN sites and the green VPN sites. You can see towards the left that there are 2 yellow sites and 2 green sites. So the yellow sites belong to the same company, and then green sites belong to the same company, but they are in 2 different geographical locations. But assuming that they're taking service from one service provider, which is represented by this orange cloud, all they need to worry about is having connectivity to one of the edge routers. And it is possible that they have different kinds of routing protocols that are running in their network. They don't have to worry about making any changes to that. They could be running EBGP, OSPF, RIP, or they could be running plain static routers, depending upon how big they are. And the service provider is going to build all the connectivity to all routers within his network, and he's going to take the responsibility of connecting all the yellow VPN sites on the left to the yellow VPN sites on the right, and the green VPN sites to the left to the green VPN sites on the right. And this is typically, this connectivity is provided using IBGP connections. Let's get into some more details about how these things work. So for implementing IPVPNs, when they were deciding what is the best way to go about providing this service, BGP was chosen as the routing protocol to provide this service. Now you might ask, why BGP? Because BGP is the only routing protocol that can support a large number of routes. If you are aware of routing, you know that BGP is the preferred protocol of choice for supporting the internet routing table, which is close to maybe 300,000 routes by now. But typically routers build their support for supporting up to 1 million routes or even more. So when we are talking of that kind of scale, BGP is the only routing protocol that can support such a large number of routes. One of the main reasons is that all it ensures is there is a keep alive message going between the peers, and it doesn't have to exchange all the information all the time like some of the other routing protocols do. So there is a significant reduction in the number of protocol packet exchanges. So that's why BGP is used. And another reason why you want to go with BGP is because it is very flexible in terms of supporting different kinds of protocols. All we need to do is say what type of information is being exchanged between the 2 routers, and as long as the 2 routers agree, you can exchange that information. Like for example, you can build extensions to support IPv6 routes, or in this particular case, the routes combined with the VPN for making them as VPN IPv4 routes. So it is very flexible in supporting different kinds of protocols. And a third big advantage of using the BGP as a routing protocol is that it doesn't mandate that the 2 routers which are BGP peers are directly connected. As long as there is connectivity between 2 routers, you can run BGP between them. Now this is a very big deal because it allows the VPN information not to be stored in the intermediate P routers. If you notice, the way service provider is going to build the network is that the P routers are really super fast routers, and you want to keep the load to a minimum in the P routers. You want to put all the intelligence towards the edge, and all the high-speed networking technologies would be handled by the P routers. So you don't want it to be bothered with doing a lot of layer 3, because any, as you know, route lookup is a very costly operation. Then another reason why you want to go with BGP is that it can carry any information attached to a route as an optional BGP attribute. You can define additional attributes that will be transparently forwarded by any BGP router that does not understand them. Basically, this means that BGP allows you to associate some characteristics or some colors to different routes that it carries. It's not just the routes, it is routes with some characteristics. And this can be very useful in coming up with different kinds of routing policies while distributing the routes amongst its peers. And one of the other things for implementing IPVPNs is the use of MPLS. As you know, MPLS combines the benefits of layer 2 switching with layer 3 routing and switching. It combines the benefits of the overlay model, such as the security and isolation among the customers, with the benefits of simplified routing that a peer-to-peer model brings. We also mentioned earlier in the presentation as to how MPLS is acting like a converged core. The service provider can build one network based on MPLS, and it can cater to customers running an ATM network and a frame relay network or anything for that matter. So it's a significant cost saving. MPLS VPN provides the capability to commission IP network infrastructure that delivers private network services over a public infrastructure. So one of the prerequisites for the service provider when providing MPLS IPVPN services is that the LSPs must exist between all the endpoints before transport connection may be established. This is very important because that is the only way the service provider can sell a service to the customer saying, no matter where your remote offices are, we will provide connectivity. And only way you can achieve that is by having these LSPs existing between all the edge routers. Now, this is not going to be a waste because you can reuse the same LSP for different kinds of traffic. It could be IP traffic, it could be L2 transport traffic. You can use the same LSP that you built. In this slide, I'm using LSP and tunnels interchangeably. I think tunnel in this case really stands for the MPLS LSP that is. Another reason is that it becomes very scalable, which means that for different VPN customers, I could be using the same LSP for transporting the traffic. So it makes it very scalable. By scalable, we mean that the service provider gets the capability to support more and more customers with less and less of provisioning within his network. Now, there are different kinds of MPLS tunnels or LSPs that you can build within your network. If you use the RSVP protocol to build, you can build traffic engineering and resource reservation based tunnels. And if you want just the best effort kind of a tunnel that you want to build, you would use the LDP protocol. This is again a service model that a service provider can choose. There are a lot of customers who will say, I want this amount of bandwidth to be guaranteed for my traffic, in which case the service provider is going to sell them the LSPs which are built based on RSVP. And then there are some customers who say, as long as I get the connectivity, it should be fine. Then they are not looking for very stringent QoS requirements, in which case they can use LDP to build the LSPs and sell that service. Now, there are some other terminologies that we need to be aware of. We are really getting into the implementation of MPLS IP VPN. So one of the terminologies that you will find people using is this called VRF. Basically, it's nothing but VPN routing and forwarding information. Then route target is another terminology that people need to be aware of. It is nothing but a color or an attribute that you associate with a particular BGP route. And then there is another terminology called as route distinguisher. We talked earlier about a scenario wherein we want to be able to use the same IP address across different customers. So the route distinguisher allows you to do that. If you see the thing in blue, this below. For every IP address that you learn, if you tag it with a route distinguisher, it makes a particular route unique. That means two different VPN customers can use the same IP address, but when I club it with the route distinguisher, which is unique for each customer, the whole thing becomes unique. So if you're familiar with BGP, you know that BGP has this community attribute, extended community attributes that it uses for transporting the routes from one peer to another. The route targets, as I said, they are carried as extended community attributes. And you can define import and export route targets for each particular VPN on the peer routers. We will see how this is very useful in the next slide. The peer routers that service the same VPN have the same route target configured for that VPN. This ensures that the VPN specific information remains only in those relevant peer routers. Now this is where the security comes into picture, which means the service provider is ensuring that there is no leaking of routes across the different VPNs. It can be associated with routes based on where they all lead to a specific site or QoS. Now let us see the example of how route targets can be used. Now let's look at the slide here. On the top we have a peer router which is providing service to two different VPNs, VPN A and VPN B, and they have their corresponding remote sites. At the VPN B site 2 is all the way at the bottom, and the VPN A site 2 is all the way to the right. Now let us see how we can use the route targets to ensure that there is connectivity between the sites of VPN A and then sites of VPN B. So you define all your route policies and VPN definitions at the edge router, right? And then you create all the different VPNs. And when you get updates from a particular site, then you send the BGP update by using the route targets. Whatever is configured as the export route target, you send that update with that export route target. And on the other side, you are going to configure import route targets. So only when the export route target matches the import route target, those routes are installed in the edge router. So that way you ensure that only the routes exported by VPN A with the export route target A gets installed in on the remote site wherein he is configured with to import route target A. So that way there is the service provider ensures that there is no routes of one VPN are not going into the routes of another VPN. So a typically IBGP update would look something like this, wherein you have the VPN IPv4 prefix, which is what is the main route that is being exchanged. As I said, this would be a combination of your route distinguisher plus the IP address, making it a very unique thing. And then you would have the next hop address. This is typical of any routing protocol where you capture the next hop address to where you can send the route to. Then it is going to contain the extended community attributes. It's going to contain the MPLS label. Basically, you need to be able to identify which VPN it belongs to when it reaches the other end. And then other standard BGP attributes like local preference, MED, ASPARC, and things like that. So let us look at the, when you're looking at a router which is providing IPVPN service, let us look at how the control plane looks. This is basically a zoom in inside the edge router. If you see towards the left, you have all the customer edge routers, and you have the pink customer, the green customer, and the blue customer, and they have the flexibility of choosing any routing protocol that they want. And there is a separate routing domain, which is a main requirement of VPN for each of these customers. Now, if you want to exchange this VPN specific information from one provider edge router to another provider edge router, you use the multi-protocol IBGP. And for that, you add the route distinguisher to each of the routes in the VRFs, and you form this big VPN IPv4 table, and this is the big routing table that gets exchanged across the edge routers, and we saw how the route targets can be used to uniquely identify each of these VPN routes. So when it goes from one BGP peer to another BGP peer, it takes these routes, and depending on the color that is associated with each of the routes, it puts them in the corresponding VPN routing tables. So in this case, when it comes, if you look at the right, when the BGP updates come to the egress edge router, it is going to put all the pink routes into pink VPN, green routes into the green VPN, and blue routes into the blue VPN. And then that in turn is going to establish connectivity with the remote PEs. So this way, all the pink VPN customers can talk to each other, all the green VPN routes can talk to each other, and all the blue VPNs can talk to each other. Now, in the middle, we have to talk about the global routing tables that are present. We need to be able to connect each of the provider routers to each other, and that is achieved through this global IPv4 routing tables, wherein you can be running your OSPF or ISS, and then you are also running your MPLS protocols to set up the tunnels. And this picture, the next slide is going to give more clarity. So you can see that the MPLS protocols and OSPF help build these tunnels between the edge routers, and each of the VRF information or the VPN information is going through these tunnels using the MPLS updates. Now, typically, how does this look when we are talking of the data plane? So previously we saw the control plane, how things are established. Now when you actually send a packet, what is it that you do? So in this particular case, let us walk an IP packet from one customer premises to, let's say, the head office, which is CE1, to a branch office, which is CE2. Now he sends an IP packet to PE1, and you can see below that the first process that happens is that you associate it with a particular VPN based on the interface on which you got the packet, and then you are going to encapsulate it with a VPN label, which is going to uniquely identify the customer. And then, as I said, one of the requirements is that you have an LSP built from the ingress to the egress. So from PE1 to PE2, you have an LSP that is built. So you add the second label, which is the tunnel label, to PE2. So basically, the packet gets encapsulated with two different labels. One is the VPN label identifying the customer. Second is the tunnel label identifying the egress router, and it is sent on this onto this tunnel. So it goes through the next router is P1, which is a core router. Now he's just going to look at the tunnel label and he's going to switch it to P2. If you are familiar with the MPLS concepts, there is something called as a penultimate hop hopping, which can remove the tunnel label if it is just if the egress is just one hop away. So that can possibly be configured, or it need not be configured. So this is up to the service provider. So once it reaches P2, the fourth process that is mentioned here, he knows that what VPN the packet represents. So he's going to strip off the VPN label and he's going to send the IP packet to CE2, because CE2 is the only guy connected to the VPN customer, which is CE1. So this is basically how the data packet flows. So we talked about this architecture in terms of the control plane, where BGP sets up all these paths, and then we talked of the data plane, wherein there's a lot of encapsulation to ensure that traffic does not go between VPNs, but it remains within the VPN. So you can see that this is quite a complex thing. So you can understand the kind of technology that is required to build these kind of routers. All the big companies are investing huge amount of money to make sure that this process is really, really fast. It has enough resiliency built into it. you need to have different kinds of processors to help achieve these kind of capabilities. As I said, the kind of scale that we are talking about is to be able to support millions of routes, and the resiliency is they want packets to switch in less than 50 milliseconds across. So this is a huge science in itself, and all the networking companies are trying to solve all these kind of problems. Now, let me just, in the interest of time, let me rush through some of the possible situations that VPN customers might run into. Now, it is possible that the two different VPN sites are in two different autonomous systems. Now, this functionality might be used by a VPN customer who has connections to several different service providers. Or the different connections to the same service provider but in different geographic regions, each of which could have a different autonomous system. Now, this is an interesting problem which is depicted in the next slide here. As you can see that the VPN customers are buying service from two different service providers, not just one. And basically the problem statement is still the same, that one of them is the head office, one of them the branch office, and they want to talk as if they are on a private network. So now the service providers need to work out an agreement wherein they can build this kind of connectivity. And typically MPE BGP is used to provide this. So there is another interesting scenario wherein the customer of a VPN service provider might also be a service provider for an actual customer. He could also be a VPN service provider for another customer. So in which case, this is an interesting scenario wherein you are a carrier of carrier VPNs. So this is also possible. It depends on the kind of service provider with whom you are getting the service, and it also depends on the kind of geographical locations where your sites are. So now one of the common questions that all service provider ask of the companies are, how do I ensure that the traffic from one VPN does not affect the traffic from another VPN? There could be a storm of packets coming from one customer which might ruin the particular router. Now, for these kind of problems can be solved by a lot of configuration wherein you can control the amount of traffic coming into a particular VPN. So there are typical security related configuration that you would use in every router can be leveraged here as well. So now one of the situations that we want to consider is how to provide access to the internet for a VPN customer. As we have always been talking about a head office talking to a branch office, but what if they want to connect to the internet? Now, the picture here in the slide demonstrates how that can be achieved, wherein you can configure static routes pointing to the customer prefix with an interface on the edge routers. So if we take the Indian bank, the left bottom, right? So he sends a packet to the edge router. He is told, okay, connect to the internet routing table which is connected off of New York, and that's the way the customer's sites can access the internet. And on the way back, there can be unique static routes for each one of the customer sites. So that is the only thing that the service provider need to be careful about. That means there has to be a unique static route to each of the customer sites. So that way, you can see that the end-to-end connectivity through routing can be built so that the customers can access the internet. Now, continuing on the topic of IPVPNs, there are many situations wherein MPLS is not deployed in some of the service provider networks. This could be in some third world countries, or in situations wherein they don't have the expertise of MPLS. So then we talk of this IPVPN lite. This is purely based on end-to-end IP transport. You can still leverage a lot of the advantages of IPVPN that we talked about. I mean, you can save the IP address space. You can reuse the address space across VPNs and things like that. But basically this is the same service that we talked about without MPLS. Right. So in summary, let us look at the benefits of IPVPNs. So here there is significant cost savings. It is much cheaper than buying a leased line network, and there is one network platform for all kinds of traffic. We talked about one MPLS converged core used by the service provider to cater to different kinds of VPNs. So that's a significant cost savings there. And there is the ease of use, which means that there is no need for specialized networking skills or IT specialists to maintain your own network. The customer has to just bother about his one connection to the service provider, and that's about it. Then the next thing is flexibility. It is very easy to adjust the size of the network as well as the amount of sites according to the changing needs of the business. So the customer feels that he can any new site can be easily added, and he doesn't have to go through the pain of getting connectivity to that site. So that's a very big deal and significant cost savings. And another advantage is the resiliency, which means since there are fewer connections to the core, MPLS also has its protection mechanisms that it has built in, like fast fade out and things like that, which is really a very big deal for the customer. Then usage-based billing. You can pay for the usage bundle and possible extra usage on your VPN and not on a per site. Single flat rate for class of service with no bandwidth or traffic mix restrictions. So you can choose a billing with the service provider in such a way that you can pay for just the MPLS SP that is built irrespective of the number of sites you have. That is again a significant cost savings. Then you can have signaled end-to-end paths. You can build traffic engineering and QoS capabilities which leverage the IP topology awareness. We talked about how RSVP can be used to build traffic engineer tunnels. As we said, we quoted the example of bank doing wire transfers versus a head office trying to talk to a branch office. So QoS is another huge thing. Then multiple layer 2 service access into VPN. Again, as I said, it doesn't matter what kind of access technology the customers are using, the service provider can build connectivity from to all the remote sites, which is a very big deal. Right, so that's about what I had. Thank you very much. So let's talk. Let's see if we have any questions.
I have already shared the questions with you. Request you to take the questions.
Okay. Sure. Is RT and RD are contained in the MPLS header? So this is a question by Gaurav Singh. Well, as I said, a BGP update is going to contain the IPv4 address attached with an RD. So that is the complete VPN IPv4 information that is being exchanged. So RD is part of the actual IP address itself that is being exchanged, whereas RT is carried as a extended community attribute. So it is like a color, as I said. It's like a coloring of the route. So although both RT and RD uniquely identify a VPN, yes, they are contained. They are not in the MPLS header as such. They are in the BGP update. Can customer have control over the MPLS VPN? So this is a question by Raghunath M. The answer is no, because that is not what the customer is looking for. He wants to transfer the burden of having to monitor all these things to the service provider. He doesn't even know anything about the VPN as such. The VPN concept is very much within the context of the service provider. It is a design by the service provider to optimize his network and provide services? So the answer is no. VPN is really within the service provider context and not with reference to the customer. Customer can only ask for a type of service which the service provider can cater to. So if there are n subscribers and all like to have different cost policies, he has to request service provider. My question is, how long will it take for the service provider to provide the required costs to the customer? The way I see it is, you are asking the customer for providing these kind of services. All the service provider has to do is know which are the edge routers which are going to have sites belonging to the same VPN, and do the right configuration in terms of what is the VPN, what is the route target, what is the route distinguisher, things like that. So it is a very simple deal in my opinion. It should hardly take a few minutes for him to configure the whole thing, because if you see a typical service provider network, he's going to have one network management station which will have access to all the routers. So it's a matter of downloading just the VPN configuration to all the edge routers which service the same VPN. So time is really not a concern here. Okay. So the next question is from Harris Padin. Sorry if I got the name wrong. But which IGP is better for MPLS, OSPF or ISIS? So typically what I have seen is that most customers go with OSPF. The only reason being that it is more popular than ISIS. If you see ISIS, it is not based on the TCP/IP protocol suite. It's open standards, right? So only those service providers which are already used to ISIS will continue to use it. Not so. I would say I would not say one protocol is better than the other. I would say OSPF is deployed more than ISIS, because both the protocols allow you to share traffic engineered information. Okay, the next question is from Anup Ramteke. As of some telecom operators are taking on the MPLS project, how does it really be implemented on the existing BTS sites, and thus in this case they will use LDP application for giving the services? So as we talked about the difference between RSVP and LDP, right? If you want the best effort services to be provided, you would go with LDP within your network. Otherwise, you would use RSVP. Basically, here the thing to keep in mind is the kind of expertise the service provider needs to have from their workforce to configure these kind of services. Okay, the next question is from Ashok S. What are MPLS tags? Will it be unique with reference to a service provider? I'm assuming you're really talking about labels. Yes, it will be unique within the service provider domain, because that is the way an LSP is going to be built. That is going to uniquely identify a VPN and all that. So it is going to be unique within the service provider for sure. Then the next question is from Faizuddin Pasha. Does MPLS packet movement differ for IPv6 scenario? No. IPv4 and IPv6 are just different transport mechanisms. It really should not matter. We talked about why BGP is the protocol of choice for this particular deployment. And in this case, I would say really the power of BGP can be seen, wherein instead of an IPv4, you can use IPv6, and the entire BGP protocol can work on this particular information without having to make any changes. So that is really that leveraging the advantages of the BGP routing protocol. Okay, the next question is from Leonard David. What type of speed is matter in MPLS VP network for different site connectivity? So the answer to this question is it depends. It depends on the kind of VPN customer. As you can see, this is more dependent on the number of sites that the customer wants connectivity for, and what kind of volume of traffic is involved in transfer and things. If you're talking of, let's say, broadcasting or a lot of video traffic, then the bandwidth requirements are different. Then your latency requirements are different. So depending on the type of traffic and depending upon the number of sites for which you want connectivity, the VPN customers would buy that kind of service from the service provider. Now, as I said, if latency is a concern for him, he would pay more and ask for more QoS services from the service provider. That's really how it's going to work. It all depends on each individual VPN customer. Okay, so the next question is from Paresh Goswami. How can we monitor the in and out traffic in a MPLS VPN in a point-to-point model? Okay. I'm going to assume that this is from the service provider perspective. So basically, the service provider is going to be a little concerned about the kind of services he's going to give to the customer. Let's say he wants to control the number of routes that a VPN customer can exchange with the service provider. He can put a limit saying you're allowed to exchange only 100 routes with me. That means they can have connectivity only up till 100 routes, right? Next thing is he can build monitoring capabilities on each of the interfaces that go to the customer side. There are many network monitoring technologies that are out there, and the service provider is always monitoring that, because it is possible that one VPN customer can send so much traffic that it can choke the entire network. So there are different kinds of monitoring technologies which the service provider is always monitoring to control the amount of traffic, and it is also tied to the billing, right? He's going to bill the customer based on this services. Okay, whether this technology is applicable for both versions of IPs, IPv4 and v6. This is a question by Govardhan SR. Very much so. This technology is independent of IPv4 or v6. In fact, both can be used. A VPN service is just a service wherein the customer wants connectivity from one remote site to the other, irrespective of whether it's IPv4 and v6. So yes, both can be used. Ramakrishna Rao has this question: which routing protocol should be selected between CE and PE? I mean, based on what factors? Yeah, this is a good question. So the way I have seen customers choose this is that if the customer is familiar with OSPF running in his network, he would want to continue with it. So the service provider is not going to put any restrictions on the kind of routing protocols that the customer will want to use. If the customer says, I want to run RIP, fine. The service provider will say, fine, you can run it over this particular link. If he wants OSPF, he can choose that. So it is more what the customer is comfortable with. That is one aspect. The second aspect is it also depends on the type of network that the customer is part of. If he has a huge network, he would go for a much bigger protocol. He would go for, let's say, BGP, because the routing protocol itself has characteristics to deal with a huge number of routes. So I would say it depends on what the customer is comfortable with and what type of network the customer is part of, whether it's a big network or small network. It depends on that. For all you know, a simple static route could also be sufficient. If a service provider is not having congestion in the core network, is there any advantage of putting QoS except for putting policy in the customer edge? So this is a question by Harris Padin Harathil. Sorry for the name wrong. So if the service provider is not having congestion, then is there any advantage of putting QoS? Definitely, there is a lot of advantage of putting QoS. Let us not forget, the service provider is charging the customer based on the type of QoS is configuring. So there is money involved in the kind of QoS. So QoS is not for reducing congestion or anything. It is for billing the customer. So these two are two separate problems. So yes, it does matter on what type of QoS he's going to associate with the traffic from the customer. Okay, I guess that is the last of the questions. Are there any more questions?
One or two more questions.
I see another question came. So this is a question from Dhanesh Sethi. When would the customer use a static route from CE to PE, and when would they use dynamic routing between PE and CE? On what basis this has to be decided? So this is a good question. So this is kind of related to what I answered earlier. Now, it all depends on the size of the customer network. So the customer is really, it's basically a network, right? So it's a head office. So there is a network within the head office. Now, if it's a very huge office and there's a lot of information, lot of departments within that office, and he wants to share all that information with a remote office, then yes, he would want to go for a dynamic routing protocol wherein he's exchanging all that information from head office to the branch office. Otherwise, if it's a very small company where he has only say some 10-15 routes that you want to exchange with the branch office, then he would go for a static route. Basically, it is the IPVPN or not. It is basically a routing problem, which is if you have small number of routes, you can do with static routes. If you have huge number of routes, you really want to go for a dynamic routing protocol. And the reason why you want to go for a dynamic routing protocol is because it can react to changes and things like that. If some link goes down, you want it to choose a different path. So those are your concerns. So it's a routing problem than an IPVPN related problem. Okay. I have another question from Raghunath M. If the customer is connecting to PE using EIGRP and is using Juniper router which doesn't support EIGRP, what will happen? Basically, we are talking of two people who do not understand each other's language. Basically, the routing adjacency will not be established, and this is something that won't happen because the customer will call up the service provider and say, I'm running this protocol, I want connectivity to your network. So the service provider is going to configure the same routing protocol that the customer is using. He is not going to configure a different routing protocol. Otherwise, he cannot charge the customer for the service that he can provide and make money. So this is a situation which is not going to happen because everybody wants to make money here. And I have another comment from Raghunath M. Thanks for the best seminar on MPLS IPVPN. Thank you very much for being patient with my talk. Really appreciate that comment. I'm hoping that the seminar was helpful for people to understand the concepts behind IPVPN and how basically people can make the customer is beneficial for the customers as well as for the service providers. I got more comments from a few other people. Anup Ramtekit says thanks a lot. Ashok says thank you so much. It was very informative. Really appreciate the share some information or clarify some of the doubts that you had about IPVPN. Thank you very much. All right, I guess that's the end of the session.
Yes,
thank you for listening to me.
Yeah, now
that will be the end of the webinar.
Thanks, Raghu, for such an informative session. Thanks to the lovely audience for making this webinar a huge success. Recording of this webinar will be available on techgig.com by tomorrow. We are also delighted to announce the next webinar series on social media. The first session in the series is happening tomorrow at 5 p.m. Topic for the webinar would be social media metrics, with what, when and how much to measure. Hope to see you all tomorrow at 5 p.m. Thank you.